Welcome to our second colloquium in the new colloquium series, and I'm really pleased to introduce Joe Atlee, who really needs no introduction here. Joe arrived, I think, I looked,
okay,
and I think in Waterloo in 1993. Is that in January
Close.
1993, at the best part of the...
92, but I didn't start here. I started in BNR.
At BNR, okay.
Yeah.
So you did arrive here in January 1993, right after your PhD at the University of Maryland, and I think I first encountered her as the first director of our software. At that time was the software engineering program, the new software engineering program, which is now an enormous enterprise and one of our flagship programs. She has recently had a strategic network grant with NSERC, which I think called Nexus, if I got it right.
Very good.
Spelled differently.
Very good, yes.
The spelling. And I think it brought in something like $17 million involving GM, IBM, and another company that I can't remember, and researchers here, Hamilton, and all across the country. It's quite something. I think this is work that will intersect with what we're about to hear today, so I give you Joe Atlee. Thank you.
Wow, thank you. Thank you for the warm introduction. So I do co-lead a large effort in model-driven software engineering, where we try to support the use of models as being the core asset that software developers would create, and then you could derive code from that. You could analyze the models directly. You could derive test cases from models. The Waterloo portion of that project supports product line software development, where what you want to develop are families of related software systems, which you can imagine would be critical in the automotive domain, right, where they are developing lots of automotive models every year and want to facilitate that development. So this is actually going to be work. Some of it is new, some of it is work in progress, some of it is actually quite old, because the feature interaction problem itself is old. And this is work with current students, postdoc, and former students. So I'm going to start with some introductions. What is a feature? Let's introduce. What is a feature? What are feature interactions? So a feature is simply, you can think of it as a unit of functionality, right? Some added value that you would like to add to a system. And features are becoming a criteria that software developers used to decompose a system into parts. So in software engineering, we're often looking for ways for how to take a complex system and decompose it into smaller problems, where the smaller problems are easier to tackle, right? And you've seen other types of components, modules, classes, objects. So feature is another type of decomposition. It's a nice one in the sense that it matches the mental model that a lot of stakeholders have about a piece of software, in the sense of it being visible functionality or visible added value to a particular product in a way that other components don't. So customers will select one product over another because of the features that it supports. Customers will pay extra money for features. So, but software developers, what we care about is that it's a nice way of decomposing problems into pieces. And in this case, it can be pieces that can be added to software incrementally, right? And so it's a nice way of supporting incremental development of a software product. Okay, so that's sort of feature-oriented software design. An extreme form of feature-oriented software design allows for the development of products simply through the assembly of features. So you can imagine a collection of features that you want to support. You can even model all the features and their dependency as a way of capturing sort of the whole product space that you could produce from that collection of features. And you can derive individual products by simply selecting whether you want a feature in your product or not. So given your entire space of possible products, you can start selecting features that you want, features that you don't want to talk about a particular product. So you've got this description of the possible products that you can build. You might have a repository of implementations for individual features. And in the ideal case, you would have some mechanized means of selecting features and assembling the pieces into products. Okay, so you can understand the appeal of this way of developing software because it's a way of rapidly deriving lots of products from a collection of reusable components. Okay, so it supports rapid development. It supports systematic reuse of pieces, and lots of companies operate this way. They are developing families of products. They don't want to start from scratch every time they're developing a variant of a product. They want to reuse what they have as much as possible. They want to derive the ability to derive products and customize them for customers as much as possible. Right? This is their way of expanding their customer base by appealing to individual needs. As I mentioned, the project that we have is with GM Motors, and so we're talking about product lines for automobile software. They have sort of the added complexity in that they are developing products every year, right? They're developing a suite of new products every year, and that's not a timeline that is very flexible, right? Because the competition is developing products every year. So you've got timeliness, you've got safety criticality, right? Because these are systems that are carrying people at high speeds, and there's a risk of accidents, and they're commodities, right? So a lot of other safety critical systems, aren't commodities. They don't have to be priced at a point where regular folks like you and me can afford them. So they've got a collection of constraints that is quite unique for product lines and for safety critical systems. Okay, so this is all the upside of feature-oriented software development. The downside is that when it comes to, while we like to think about these features as being orthogonal units of functionality, in the end, we have to be able to assemble them into a coherent system. And in that process of integration, we find that the features sometimes interact with each other in surprising ways, right? So features that we thought were orthogonal, they might conflict over actions that affect some shared variables. It might be that the features operate fine in isolation, but you put them together and they start violating global invariance of the software system. Or it might be that suddenly new behaviors emerge that weren't present in either of the features. So this is a classic software integration problem. Okay, so this is a feature interaction. The feature interaction problem is the fact that the numbers of interactions that have to be considered is exponential in the number of features. So any developer that's going to really care about interactions is going to have to think about and consider all the possible ways that features can interact, right? They're going to have to think about all possible combinations of features and explore them and determine, is there an interaction? Is there a problem that needs to be fixed? If so, let's fix it. And then we have to test whether the fix is correct. And because there's a an exponential number of possible interactions to consider. If there's, it gets to the point where the maintenance or the management of these interactions sort of dominates the entire development of a feature, right? Where the development of a feature might be some core functionality that this one feature is adding, plus a bunch of exception code to deal with each of the interactions that needs to be managed. So this is really the feature interaction problem, right? How to develop software in an economical way and be able to add features easily to our repository without being overwhelmed by interactions. Okay, so I'm going to talk about some approaches, some research that has tackled different aspects of the problem. So I work at the requirements level, mostly in terms of modeling and automated verification of software. So I'm going to look at how to model requirements in a way that supports feature orientation, feature modularity. Look at some work that we've done in the way of analyzing features and verifying them, looking for interactions, and then also looking at some resolution strategies. Okay, so to get back to the title of the talk, right, the good, the bad, the ugly, starting with the good. When most people talk about feature interactions, it's always, feature interactions are bad. They complicate the development problem, and they're almost always introducing behavior that we don't want in the system. But that's not entirely true. There's a lot of interactions that are desired. Some of them are planned, right? And so there are times when a feature is introduced for the sole purpose of extending or overriding an existing feature. So there are there are noises coming from the vents, is what there are. There are advanced cruise control variants that override basic cruise control. There's a feature, prohibit navigation, that keeps drivers from using the navigation system while driving. And then, of course, other people have for sale a prohibit navigation override, because drivers do want to use their navigation system while driving. So there's lots of cases where features are introduced solely for the purpose of overriding or extending existing features. It may be that features, you put them together and they behave in new ways, but the new behaviors, the emergent behaviors are in fact okay, or they're desired, or they're harmless, or they're certainly not worth changing. Okay, and there are also cases where we introduce a feature for the sole purpose of resolving an interaction. So Toyota, when they were having their problems with unexplained acceleration, they introduced a feature brake override that overrides the case where the driver actually presses the acceleration pedal and the brake pedal at the same time, right? So you'll see features of this sort. So in any case, there are going to be times when we actually want interactions, and it would be nice if we could explicate these in our models, in our requirements documents. And it would also be nice that if we did do some automated analysis, that analysis sort of knew which interactions were intended and didn't report those as part of the results of the analysis. Okay, so Porya Shaker, who is sort of in the process of graduating, he defended his thesis, is still making changes, did some work on creating a language for expressing requirements, so it's, adapting state-of-the-art requirements modeling notations to support feature-oriented requirements. So In particular, it supports feature modularity. It provides some constructs for expressing intended interactions. It has a lot of other nice features that I'll talk about, but these are the ones that are really critical to this talk. And the other thing is that when you put features together, the result is a product line rather than individual products, and this will facilitate analysis of an entire product line instead of analyzing individual products. Okay, so I'm not going to talk about this slide a lot. This sort of captures some of the state-of-the-art aspects of requirements modeling, in the sense that you have not only a model of the software that you're developing, but also a model of the environment that it's going to operate in. And so there's sort of a concept model of the environment. You can think of it as an ER diagram. You can think of it as an ontology of the inputs and outputs of the system. The system itself, we're going to model in terms of state machines, and we're going to decompose them by feature. So you can think of it as a state machine per feature. And the features are going to read input from the world, and they're going to output commands that change the world. Okay, so each feature is an extended finite state machine. It's kind of like a Mealy machine, but with very rich input and output alphabets, and infinite alphabets. It's got states that reflect sort of the state of an execution. It has transitions that are triggered by events in the world model or conditions in the world model. And if a transition is fires, then there are some actions that perform changes to the world. So there'll be some assignments to the world. So this is a state machine, a truly simplistic machine of basic driving. It's got some behavior that focuses on acceleration of the vehicle, of braking of the vehicle, and steering. So it takes commands, events from the world in the form of driver commands, and makes some changes to the world in the form of changing the vehicle's acceleration and speed. Okay, so you can imagine in the course of developing your product line, you're implementing features one at a time. For the most part, a feature is going to introduce new behavior, and for the most part, it's going to be modeled as a new machine. Okay, but as I mentioned, every once in a while, you'll have features that want to extend or override existing features, right? And this has the effect of changing the behaviors of those existing features, right? They may eliminate behaviors or substitute, override behaviors in existing machines. So these cases, right, tend to be our interactions, our intended interactions that we want to explicate. And even though the effect is to change behaviors or remove behaviors, in FormL, we're going to model them as additive extensions to the machines that we have, right? And so we're effectively going to be modeling this as machine fragments, so state machine fragments that we will attach to the machines of existing features. Okay, so that's how we're going to do. That's how we're going to model intended interactions. It has a nice effect that evolution of the system is additive, right? So we're always adding things to our model instead of having to make changes, which can be harder. And it will support product line extensions in the sense of these new features might be optional, and if they're not present, then you want the original behavior there anyway. So it's nice to think of new features sometimes as variation points, as additive additions. Okay, and so once you've got the notion of being able to model things as fragments, you might as well support the modeling of new behaviors as fragments as well. So it may be that you want to model new behavior where in contexts where it's best expressed as an extension to an existing feature. So for example, cruise control has a lot of extensions. So cruise control that takes the speed limit into account. Cruise control that takes road curvatures into account. Cruise control that takes into account whether there's a vehicle in front and we're getting dangerously close. And so those new features are sometimes best expressed as extensions to basic cruise control. Okay, so just to give a couple of examples, this is a model of cruise control. It extends our original, very simple, basic driving machine. The extension, the context of the extension is the state on, where the vehicle is on and running. And what it does is it adds a new orthogonal region of behavior. So in addition to acceleration and braking and steering, it now has this cruise control extension that's going to be monitoring the speed and trying to maintain the speed at some driver selected value. Okay, but instead of having to remodel the behavior of getting to the state where cruise control is active, we can simply describe sort of the context of existing machines where that it affects. So this is one example. Another example is a headway control. So this is a variant of cruise control that takes into account trying to avoid a collision with a car in front of it by maintaining a safe distance to the vehicle ahead. So this feature does provide new behavior. Provides new behavior. In the form of yet another extension to cruise control. It also is an example of a feature that has to override behavior in an existing feature. So if there is an object ahead of the car that is dangerously close, then this feature takes priority over cruise control and determines the appropriate acceleration. Okay, there's lots of different constructs in the language for describing priorities, for describing overrides, for describing even underrides. But this is just to give you a flavor of what we're trying to do here. Okay, so given a collection of features and a collection of fragments that extend features, when you put them together, you get a model of an entire product line. So it's not a model of an individual product. This would be a model of a product line in the sense that it's a model that includes all of the features that we have specified. It may not even make sense, right? There could easily include combinations of features that are prohibited. Okay, and so in order to let me put it this way. Okay, so given the fact that there are going to be features that are optional, it's nice, we use presence conditions to realize and enable the behavior given the presence of that feature. So anytime you see feature-specific behavior in this model, for example, all of the green in this model, I don't know if you can see the colors very well, but all the green in this model comes from the cruise control feature. All the green behavior is conditional on a feature variable that represents the presence of that feature. So if the feature is present, then the variable is true, and that enables this behavior to possibly take place. If the feature is absent, then those transitions are unreachable. So it's a way of being able to capture in a single model all of the features and to be able to differentiate among the products by setting the values of these individual feature variables. The other advantage that 4ML has with this composition is that it's commutative and associative, and so that will come into play when we do analysis, in the sense that we can put the features together into a model and analyze this model without worrying about the order in which the features were composed. Whereas if feature order made a difference, then the analysis would have to possibly analyze multiple different orderings. Okay, so this is sort of our quick overview of a modeling language that supports features as first-class citizens. It allows the explication of interactions that we want to happen, and so this will come into play when we do analysis. There's some nice properties, nice features of kind of overloading of features, but there's nice facilities for modeling features as fragments, and then the result of putting features together is a product line. Okay, so that's sort of our modeling work right now. Okay, so progressing into the bad. The bad, of course, are the undesired interactions as opposed to the intended interactions, right? And so to give a couple of examples, I hope none of you have a 2010 Toyota Prius. So that particular vehicle had a new braking system where, in addition to hydraulic brakes, they also had regenerative brakes where they tried to take advantage of the kinetic energy that was being lost during braking and turn it into electrical energy and store that into batteries. Okay, so you've got this complicated braking system. You've got anti-lock brake system, which is a fairly old feature at this point that tries to maintain stability and steering during panic braking, where the wheels might lock, and instead it varies the brake pressure. Okay, well. In this particular make and model, there was an interaction between these features where the braking force after ABS was actually reduced instead of being greater. Okay, so as a result, vehicle stopping distance was increased. There were reported crashes and injuries and a recall of probably 150, 180,000 vehicles. Okay, so that was one vehicle. Another example affects actually most cars. So most advanced cars have cruise control. So this is our feature that tries to regulate speed at a constant driver set value. You've got traction control, so this is a safety feature, a stability feature that applies the brake when the wheels start to slip. Okay, and there's an interaction here, because if the wheels start to slip, then the car applies the brakes. Okay, and the cruise control is going to sense, well, the car is slowing down, and so it's going to accelerate the engine. And what happens is that once the wheels stop slipping and actually catch, there's this sort of sudden acceleration of the vehicle. And so I don't know that this has resulted in crashes, but certainly, drivers are uncomfortable, and they have reported that the vehicle is difficult to control. And so what would you imagine the resolution? Yeah.
And then on top of that, because the car is doing more, the driver is probably paying less attention, so it's more surprised when things happen.
Well, for sure, the driver is going to be surprised, right? The driver usually doesn't really even know about traction control, right? It's just there, and cruise control they at least set, but yeah, the driver is going to be surprised. And so how would you imagine to resolve this interaction? That's exactly right. And so if you look in your manual, if you look in your driver's manual, you will probably see, don't use the cruise control on slippery roads.
Can't you just have that be automatic though? The traction control turning on makes the cruise control turn off?
Well, so I think there's a little bit of that going on here, right? In the sense that the traction control has priority of cruise control. It's just that, once it has taken effect and done its job, cruise control is there, ready to resume the speed. So, but yeah, maybe it would be nice if it detected that cruise control had been overridden and that the process of reestablishing the speed could be gentler. Yeah. So there are bad interactions, and as I mentioned, one of the complications of developing in a feature-oriented paradigm is that you want to be able to detect these and to detect them in a reasonable way. Okay, so at the essence of what's happening, right? What are feature interactions at the essence? Is you've got a collection of features. They've been developed in isolation. They've been verified in isolation to work. And so each feature sort of satisfies its specification, satisfies its feature-specific properties. But when you put the features together into a product, the product doesn't satisfy the conjunction of all the features. So it sounds like a problem for formal methods, right? And the formal methods community jumped at this problem and have developed, taken a lot of their techniques and applied them to feature interaction. The one that I've been working on uses model checking. So model checking is an analysis technique. It applies to software models. It also applies to code. What it is effectively is a massive search problem. So this is going to be a gross simplification, but what model checking does is it basically generates all the possible execution paths through a program, through a model, and tests each execution path to see whether it satisfies a particular property written in temporal logic. Okay, and so you run it through the model checker. The model checker does this case-based analysis. If the property holds, then this supposedly means that it's been searched on every possible execution path from every initial state, and this means that it holds in the model. And if not, then it produces some counterexample. It produces an execution trace that violates the property. Okay, so you can use this to detect feature interactions by, your software model being your composition of features, the properties being the individual feature properties, one by one, and finding which properties fail. So I've done a lot of work with doing this kind of analysis on individual systems. So in the 90s, we were model checking flight control software. We were model checking telephony features. We were model checking the operational flight software for a U.S. naval plane. And we were finding errors in models and in specifications that had been thoroughly inspected. Right? These were specifications that were used in a lot of software inspection research, and so we were getting fairly good specifications to start with. But we were finding things like if the navigation system is detected, if the navigation system knows that input sensors have failed, right? And so it's using stale data, and so the airplane doesn't really know where it is. The weapon delivery system could still bomb on coordinates. Okay, not an ideal combination. Okay, and there were special weapons, which was sort of a pseudonym for nuclear weapons. Special weapons. Okay, yes.
Do you want questions now?
Sure.
So I was just wondering, in this process of generating counterexamples, I can imagine that there are some counterexamples that make people queasier than other counterexamples, like that's a great one. Do you need to tailor the search space? I mean, if you find some counterexample that's really esoteric and you're like, it's never going to happen, maybe you're not concerned.
Right.
Is there any work on like trying to find sort of the most salient counterexamples?
Yeah, so the counterexamples are simply traces. They're simply evidence that your property fails, right? Whereas it was the property itself, right? That particular combination, that was a particular property, right? And so all the counterexample does is gives you evidence, right? That yeah, it really is a problem. It's not sort of a false positive, and B, it helps you debug. Right, because now you sort of know the execution trace that it took, and maybe you can fix it somewhere along that execution trace. And so, so it really is a question of what properties do you care about, and that you have control over. Yeah. So we're recently, because we're doing this product line work. We want to do model checking of product lines, and so there has been some advances along that through from the University of Namur, where the input to the model checker isn't a model of a single system, but a model of a product line. Okay, still have the properties that you want to verify. Now, if you put that through the product line model checker. What you get is if the property doesn't hold, you get sort of the list of products that violate the property, and that's nice because you can either try to fix the problem, or if it's late in the development cycle, you can simply forbid combinations of features that violate properties. So it's a nice way of finding problems, and there are easy fixes. In the case of simply forbidding feature combinations that are problematic. Okay, so this is what what we've been working on. Question is now, we need to be a little bit careful with the properties that we are formulating, right? Because now it's not necessarily going to be some property that holds for all possible products, right? The properties, if they are properties that are specific to features, then we want them to only really be evaluated when the feature is present. And we want to accommodate these intended interactions. We don't want an analysis technique that reports to us intended interactions as problems. Okay, so Sandy recognized, this is Sandy's thesis work. One of the things that Sandy's recognized is that the intended interactions, the effect that they have in analysis is that they sort of determine whether a transition executes or not. And so there'll be transitions that are enabled in any situation. But what an intended interaction will do, at least, it might forbid a transition from executing. And so we can articulate our properties to be conditional on, does the transition execute? And if the transition executes, then is its post condition true at the end? Okay, and so that's the direction that we're looking at. So given a product model, you can, for each transition, write these properties to say if the transition executes, then its post condition should be true in the next state. And that won't be true if there are unintended interactions between features that we don't know about. It won't be true if the model is not deterministic. It won't be true if there are conflicts. Okay. The other nice thing about this approach is that the properties can be generated automatically from the model. Right, because we're given effectively a finite state machine model. We can, for each transition in that model, automatically generate these properties, and that's pretty important because it's hard enough to get practitioners to write state machine models. It is impossible to get them to write temporal logic properties that they want to hold of their product line. That's just not going to happen Probably not even in the far future. And so being able to generate the properties for detecting interactions is pretty key. Okay, so some of this is work in progress. Shoham Van David has been working on improving the performance of the back-end model checker. And so she's done work so that the back-end model checker is at least an order of magnitude faster than the original one that we were using. This translation from the 4ML product line to a model that can be model checked is ongoing work, because that's a fairly complicated transformation, because you're starting from a model that's got very rich data types and a complex multi-step execution semantics. And the models that these model checkers take tend to be very simplistic, right? So they're Boolean data types or variants of Boolean data types like integer ranges and enumerated types, and they have a very simple execution semantics. So we're at the stage where we've got, we pretty well understand the transformation rules that need to happen, and that's just being automated. Okay. So summary here is that properties can be generated automatically from the product line model, and then the analysis does this case-based search and detects interactions. But because of the way we formulated the properties, only the unintended interactions will be reported. Okay, so that's the good, and this is the bad. The ugly is a scalability issue, right? This issue of, okay, there's an exponential number of interactions for a given number of features. Okay, and so that's only, exponentiality is only a problem if you actually have a large number of features. Okay, right? Well, when I started this work in the early 1990s, telephony was up to 1,000 features in their exchanges, okay? And we heard a talk earlier today that was talking about 10,000 features in automobiles. Okay, so now it's starting to get to be a problem. Okay, and it isn't just that there's a large number of features, but a product or a system that really needs to be considered might actually be a combination of feature-rich systems, right? And so if you think about a telephone call, there's actually lots of different systems here, right? There's your phone, and it has features, and your provider is trying to sell you features, and maybe you forward a call to your work number so that you have access to that features, and so you can imagine a telephone call that involves 4 or 5 different collections of features that can affect that call. These features can come from multiple providers, and so you're not going to have a centralized solution for resolving interactions. And there might actually be multiple versions of the same feature, like voicemail. Okay, so there's lots of features, but maybe that's only that's not going to be a problem if there aren't a lot of interactions to deal with, a lot of interactions that have to be actually addressed. Okay, well. In some domains, features are highly interactive. That's certainly true in telephony, right, where you've got a lot of features, and they're all trying to control a very small protocol, very small set of signals. Okay, but even though it's extreme in telephony, the number of interactions is actually problematic in a lot of other domains. Email, there are lots of interactions among very few features. Automotive looks like there could easily be lots of interactions, simply as features share sensors and share actuators. There's lots of features that try to control the vehicle's speed. There's lots of features that try to control braking. Okay, there's lots of different types of interactions. I'm not going to go over them, but just recognizing that we're not going to have a single means of resolving this problem. And they can be introduced in lots of different phases of the development cycle, right? So I deal at the requirements level, because I'm doing automated model checking and I want small models. Okay, but at the design level, more interactions can be introduced because features share resources, they're sharing I/O devices, they're sharing protocol signals. Additional interactions can be introduced at the implementation because code can be shared as soon as one feature recognizes that it can borrow functionality from an existing feature. Okay, so hopefully, hopefully you're at least convinced that this is a hard problem. Lots of features, lots of interactions, multiple types of interactions, introduced in lots of different places. What are we going to do? So the best work that I have seen, not just mine, in general, the best work that I have seen along these lines try to tackle the problem at a very general sense, right? They use the architecture to coordinate features in a way that the architecture doesn't know what features it's coordinating. It just coordinates the features. There's other work that uses it tries to resolve interactions through feature composition, right? In the sense, we're going to try to, through the semantics of how we put features together, simply remove through a resolution strategy a particular type of interaction. Okay, and so in the end, we're effectively synthesizing products that are interaction-free, at least with respect to the particular interaction that the composition operator resolves. Okay, so we've done some work on conflict-free composition, where the resolution strategy that we're trying to achieve is given a bunch of features, they're executing in parallel, where they want all to execute at the same time. Let the behavior be, the maximal conflict-free set of transitions that can execute, right? And we can formulate this as a transformation process where we're taking a collection of features, a priority among the features, because this is how we'll resolve conflicts, and produce an integrated system of the features where features can execute together if they don't conflict, and you can encode conflict in the enabling conditions of these transitions, where what you're saying is that the post conditions don't conflict. And then individual features execute either because they're the only ones that are enabled, or because there was a conflict and this feature had higher priority, right? And so you can transform a collection of features into a composed model.
T1 and T2 as well.
Yep. Yes.
Yeah.
Yes, you are correct. That's not a feature interaction, that's an error. Might be on the next slide too. All right, so this is a simple resolution strategy. Yep, there it is again. A more complicated resolution strategy looks at a case where features have two types of outputs, right? Where they might be changing have actions that change the world, but they may also assert assumptions about what doesn't change. And so now you've got four possible ways that all these outputs might conflict, right? The actions of the features might conflict. Actions of one features might conflict with the assertions being made by the other feature. A feature might be making some assertions that simply aren't satisfied in the current world model because of previous actions that have been executed, or the assertions themselves might conflict. Okay, and so you can again have a general resolution strategy for dealing with these kinds of conflicts. So we were, as before with the previous slide, you can resolve conflicting actions by priority. So you want the maximal set of features to execute, and if there's a conflict, let the higher priority feature proceed. When it comes to actions violating assertions, we resolve these also by priority. And so if actions have the higher priority, this feature has the highest priority, then it'll execute actions that violate the assertions. Assertions, we simply allow them to proceed. Right? We allow if the only conflict is in the assertions that a feature transition is making, we let that proceed. And this is not unlike, for example, access control policies, where if the policy changes, you don't suddenly shut down the previously proved accesses. Right? If you have a file open and someone has changed the permissions of that file from under you, that you can still use that open file, but once you close it, you can't reopen it. And so in the same sense, you can assert these assertions, and they will guard future actions, but they won't necessarily start to undo previous actions. And this has a nice property that we can assert conflicting assertions. We can assert unsatisfied assertions without breaking the analysis, right? Like normally you can't work with a collection of assertions that are mutually not satisfiable. But if the only thing that the assertions do is guard against actions, then what you care about is, okay, what are the assertions? What is their priority with respect to the actions that are being that a feature wants to perform, and that's resolved by priority. Okay, so the nice thing about these general resolutions is that they are feature independent, right? They are a way of resolving interactions that don't care about the specific features. And so in that sense, you can address the scalability problem, because you're not having to sit there and consider each individual interaction in isolation. The downside is that the resolution's not going to be perfect, right? It's going to be a resolution. It means that you're not going to have a conflict. That's all you're really getting away from is, you're getting away from these conflicts, these interactions. It's a resolution. It tends to be reasonably good if you've got a good sense of, in the previous case, of the priorities among the features. And so if you're in a situation where you've got a small product line, you have a small set of features, you know all the combinations that you're going to sell, you probably can get away with perfect coordination, right? Where the developers actually consider each interaction individually and provides a perfect fix for an interaction. Once you start getting into systems that have lots of features, maybe all the combinations are known ahead of time, maybe not, or maybe they're just too many to deal with. Then these general resolution strategies are nice. And certainly in cases where you really have no idea about what features you're dealing with, then these general resolution strategies are almost essential. And even if they don't produce quality resolutions, they will at least produce predictable resolutions, which might be all that we can hope for when talking about interactions between features in open systems where anybody can add features or anybody can add apps. Okay, pretty good. So in summary, our work has been looking at all these different approaches. We've got a modeling language that I'm at least quite happy about, in that we're able to model features as separate modules with at least some mechanisms for specifying intended interactions. We want to compose them using these smart these smart composition techniques that employ general resolution strategies, and then take the result of that and give that to the model checker to look for what undesired interactions remain after at least some of them have been resolved through composition. So still working. We're working on new resolution strategies now, and I kind of sort of mentioned sort of the state of where we are with respect to automatically analyzing feature combinations. All right, that's the full thing.
Okay, so can you design iteratively in these cases? So could I say something like, if I add this new feature, I'm going to have to change half my modules, so we don't want to add it? Or you can say, if we add these 3 features, we might as well do it at once because it's the same amount of work.
So the whole one of the main motivations of feature-oriented software development is to support iterative development. And parallel development, right? And so we divide our increment even into these modules. We give the features to different teams, and the teams can work separately, and then we put things together at the end. So we probably wouldn't, care about putting things together.
It seems like you have to specify the interactions in this model. It doesn't seem like you can discover these interactions from your model.
Okay,
or
so
can you?
Yeah, so what we're trying to get away from is let's not specify the interactions, because once you're in the mindset of having to specify all the interactions, you lose all the benefits of feature-oriented development, right? You are effectively specifying the whole thing, right? And you've separated your interactions here and your feature modules here, but you're effectively specifying the whole thing, and so. What we're trying to do is not specify the interactions. Either specify the intended ones, and these tend to be much fewer than the unintended ones, right? But these are the intended ones. This is the I'm developing call delivery, call ID blocking for the sole purpose of overriding caller ID, right? So these are the intended ones. Use your analyzer to detect the ones that you don't know about, or ideally. Through composition, resolve some of them, detect what's left, and then you can think about whether you want to fix those. And I would take that approach rather than trying to, up front, work out all the interactions, consider them, fix them, right? That's exactly what we're trying to avoid.
If I might add to this, there's also the effect that as a group of people are doing this modeling, sometimes they think of things that they wouldn't think of unless you're forced to work out the details in order to write them. So even if you never go to the formal setting, just the act of sitting down and building these models help people discover things that they didn't know about it and were not able to see before.
Yeah.
Frank.
A model checker typically gives one counterexample. Does this PL model checker give one invalid configuration, or a set of related invalid configurations, or all of the invalid configurations?
It gives all of the invalid configurations, and it gives one trace from one of the invalid configurations. Yeah. So I mean, it's nice to know all the invalid configurations. Unfortunately, with the counterexample, you only have information about how to fix one of them, and maybe it'll apply to multiple cases. But yeah.
That counterexample will only work in one of those configurations, or I don't understand how the one counterexample relates to a whole set of invalid configurations.
It doesn't. So we don't exactly know whether there is a systematic process by which this particular model checker chooses which configuration to report the trace from. We've done some preliminary investigations, and it looks like it might be the largest product that violates the property, but we don't know. But it does tell you all of the products that hold the property and all of them that violate it.
So maybe a bit off topic, but do any of your car companies discover they have two different groups actually working on the same feature and they don't realize it?
I don't know the answer to that.
Well, like when one division is moved into another, or they purchase another car company, I'm just
Right.
curious if there's a feature alignment problem that also
So, I mean, it wouldn't surprise me in the sense because they don't develop all the software themselves, right? So they procure a lot of the components, and the components come with features. And so it wouldn't surprise me if there is some duplication just because a vehicle involves subsystems and maybe from different suppliers, and those subsystems have a common feature or feature variant, right? So
happen in industrial software, though. That
yeah,
you have multiple things within a big company that do exactly the
Yeah.
same thing, or almost.
it's probably most likely going to be a variant, and then there's a question of how to deal with the variants, right? Whether to turn some off or to, probably in this case, to turn some off.
In combinatorial testing, a typical assumption is that only few features interact at a time, typically binary interactions. And also the diagrams that you've shown, there are tons of binary interactions, but nothing else apparently. Now you have a tool which can analyze all configurations in a sound way. Do you have some insight of whether this holds, whether this is a good assumption, and whether, for example, binary pairwise testing would be sufficient to detect these interactions?
Yeah, so because we don't have this quite implemented, I don't know the answer to that in the automotive domain. We have done some work in the telephony domain, and you're right. We had a collection of features that we did both, right? We did pairwise analysis as a stepping stone towards full product line analysis, and we did not detect any new interactions through the full product line analysis. And so I do think that that's still a way of tackling the scalability issue at the analysis step, where it makes sense to do pairwise and then exclude those before doing a product line analysis to see whether there's other additional interactions.
I have a question about the example that you gave from Prius. I wonder whether there's public information available to what extent this interaction, what was the cost for the interaction? It seems to me that essentially, putting together ABS and
This
this
hybrid braking.
Exactly. The truck. No, that was the second example.
Yeah.
Exactly, regenerative braking and ABS. It seems to me that should have been essentially detected during testing. So I wonder where in the end the critical lapse happened. Was this in the design? Was it in the assembly? Was it, we have examples recently in Chrysler where a vehicle had switched sensors for the side bags, right and left. It was actually this year in our assembly plan. And those things can happen actually in the assembly plan. They can be well designed, but the production process is not well executed. So the question is, where those things happen.
Right. So there are public documents that talk about the Prius example. The companies, try to say as little as possible in those documents. And so what the company did say was that the hybrid braking was complicated, right? So this was the merging of the regenerative and the hydraulic braking, and that the solution was that they were going to fix that code to work in the situation where ABS is activated. So they made it sound like it was an interaction with ABS, and that they were going to have to come up with a fix about what happens when those two features are activated at the same time.
Yeah. Do you have any sense how many interactions are actually pairwise and how many are multiple feature interactions? So for example, maybe if you have 3 features and there are no interaction in the pairwise manner, but if you put them 3 together, then you get some unexpected behavior.
Yeah, so the question was, I don't know if that mic is working. The question had to do with pairwise versus interactions that are revealed only when larger collections of features are involved.
But my question was actually, do you have a sense what is more often?
What's more often?
If you covered all pairwise interaction,
Yeah.
maybe you never need to look at multiple
Right.
interactions.
The direct evidence that I have is really only in the telephony domain, because we're not at the stage in the automotive domain where we've had been able to translate lots of features into models that can be analyzed. But in the telephony domain, it is by far mostly pairwise interactions, or certainly pairwise interactions, or multiple features do not contribute in very many additional interactions. I can name like 1 or 2, but they tend to be forced examples, right? That's right. That's right. That's right.
I don't know, 80%.
That's exactly right. Yeah, and so Christian was asking a similar question, right? And for effective analysis, what we have done in the past is let's do all the pairwise. Let's analyze all the pairwise features first, understand those interactions, address them, fix them, account for them somehow, before doing the full product line analysis. And so that finds the vast majority of the interactions quickly and cheaply, and keeps the expensive analysis at the end once you've got the obvious errors addressed.
And so I'd like to thank Joe for a really exciting talk. And,
thank you for the invitation.